Hey guys, before the video starts, quick note. I'm going to show you guys how to find drag through a spreadsheet at some point in this video. Um, this, please copy it. Um, you guys should be on view only, but it's called drag estimation in the drive. Um, just please copy this, and then there's going to be some formulas. You guys can just straight up copy them. Other things I want you guys to actually like find yourself because you guys have different designs. Hey guys, this is Nick from ADC, and today we're going to take our initial Explorer 5 sims, use what we did in SOLIDWORKS, and kind of use that stuff to reiterate on our design in order to hopefully make more accurate SOLIDWORKS designs um, with the intention of, you know, monitoring the performance of our aircraft more realistically. So to start off, we're going to open up our SOLIDWORKS model. This is the current assembly, and we're going to just go, if you probably start on the assembly tab over here. If you click over on the evaluate tab, you'll see something called mass properties. And so we want to use these values in order to determine key characteristics of our plane. So first off, the mass is 342.46 grams. As you can see, this is a little bit larger than our estimated weight. So now we actually have a weight, we can go ahead and plug it in there. And what I'm going to do is I'm going to multiply this by 1.1 because that will account for any, actually I'm going to multiply by 1.15. This will account for any glues that we add, any tape that we put on that we did not account for in our SOLIDWORKS models. If you look, um, we just have servos. We don't have any arms or anything for them to control. So those will all add weight. So because of that, I'm just going to go above what we currently have by a little bit in order to make sure that we have an aircraft that's more representative of um, what we have. So then from there, that's going to change a couple of things. So I think we're good for this right now. We'll come back to this. What we're going to do now is we're going to use some of these values from SOLIDWORKS to, what we're going to do now is we're going to use some of these values from SOLIDWORKS to estimate the drag of our aircraft, and then we're going to use that to determine our speed. So if you go to the ADC drive, there should be something called drag estimation, and it should look like this. And so I'm going to kind of walk through each of these parameters and then kind of discuss um, where we can get these parameters from and um, how we can use that to inform our design. So, and now we're going to talk about how to estimate the drag. So firstly, I just converted the cruise speed we had into feet per second. Um, just you can do a quick simple calculation conversion on Google, should show you. Then what I did is I found the altitude. You guys can just use this altitude value here. Um, as far as atmospheric temperature goes, you can just look up the historical data. Um, the place we are doing our flight tests is Britonia Park. So as you can see, this is located in Princeton, Texas. So I would just go online, look at historical weather data in Princeton, Texas for either December or February, and then use that to find the temperature. You can also go ahead and look up the elevation um, and determine it online. So that covers these two items. Then as far as getting a density would go, we now found um, our air temp, and our altitude, and that will give us the density of air. We want it in slugs for, yeah, and we want it in this unit. This is a little bit different than normally I would do everything in metric, but this calculator was made by the Aero team at DBF, so they did everything in the customary system. So we'll leave everything also in the customary system. So then, once we found this, in order to find kinematic viscosity, we need to use this calculator right here. And what we're going to do is we're going to go per second, and then our characteristic linear dimension, I'm going to use meters. So our fluid velocity, 26 meters, or 26 feet per second, sorry. And then our characteristic linear dimension will be our wing area. Our wing chord, which is that many meters. And then for fluid parameters, I'm just going to choose 15 degrees Celsius. And so you can grab the kinematic viscosity from here. And then this will give you an output Reynolds number. As you can see, it's really close. So kinematic viscosity is here. And then now basically I'm going to dive into what all of these values are. And then I'm going to go through it for the wing. And then I'm going to let you guys find the other parts on your own. I think it'd be a bit redundant to find it for all the things. Actually, I'm going to do the tail, and then I'll let you guys go through all the other parts. So first off, we need to find the reference wing, or the reference tail area. Imagine that says reference tail area. So what we're going to do is we're going to go over to our sizing, and we're going to find our planform area. So if we look over here, this is for the horizontal tail. So our planform area is 0.0257 meters cubed, or squared, sorry. And then I already went ahead and grabbed the conversion factor. So I'll just put that there. I need the equal sign to make it an equation. Okay, cool. So now we have tail area, the tail planform area in terms of feet squared. Then we need the chord length in feet. So chord is right here. And then the conversion. There we go. Thickness ratio. So the way that you find the thickness ratio, and this is kind of important, is you go to airfoil tools. And you search up your airflow. So I'm going to search up ACA 0012 as this example. And then as you can see, it'll say max thickness 12% at 30% chord. So what that means is that the maximum thickness, which is this dimension, is 12% of the chord length, and that occurs 30% into the chord. So 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3. So at this point, this is 30% chord. This is where the maximum thickness of 12% occurs, just to kind of visualize it. As you can see here, 12% is at 41.3 chord. If I change this to a NECA 0010, you'll see the maximum is 10% instead. So that just kind of gives you a ballpark of kind of what that thickness ratio is. So we have our chord thickness ratio, span. We can also just find that. Pretty simple. Then Let me add my conversion factor. Aspect ratio, we also already defined 2.5. Then we need to talk about exposed planform area and wetted area. So exposed planform area is just your planform area. So you guys don't need to worry about this because all of your planform area is exposed. So you can just make that equal to your reference area. Then the way you find your wetted area is through SOLIDWORKS. So I'm going to show you that now. So this is our assembly. So wetted area is all of the area that is exposed in a sense. So as you can see on this tail, as air is flowing this way, this entire surface is going to be touching air. Air is going to be flowing over the top, air is going to be flowing in the front, air is going to be flowing under the bottom. And then also, air is going to be flowing over that side. Now, if we actually open up the horizontal tail, it's going to take a bit to load. You can see that we highlighted this side and this side, but not this side. So what we can do is we can go to evaluate, mass properties, and we can find the surface area. So that's 358.09.31 square millimeters. 58.09.31. I believe that was the right number. Okay, so now we have that surface area. Now what we need to do is we need to take off this face, so we can just hit measure and find the area here, 874.46. And then we also need to take off the area from the little holes. So that's 19.63. And then I'm going to put everything in parentheses because now we need to convert from square millimeters to square feet, and then divide by that value. So we'll just go ahead and divide. And there we go. We have now our wetted area. Now, Reynolds number is going to be calculated for us. Skin friction coefficient is already calculated for us. Form factor is also found for us. And then now we have interference factor, which is the last bit. You guys don't need to worry about any of these. Just accept them as they are. If you really want to know, you guys can DM me and I can give you guys an explanation. But otherwise, that's how you do it for finding the reference dimensions. As you can see, we now have horizontal tail Reynolds numbers. And eventually, kind of the idea is you would have a full buildup of drag. So I'll show you what that looks like after I finish all of these. And really quickly, just before we go on, I just wanted to make sure that I mentioned this. I made a mistake. You should have, because this is the surface area responding to the holes, and we have two of them, so you should multiply that by 2, and then also because we have two horizontal tail bits, at least for my aircraft, then you should multiply this value, the entire value, by 2. If you just have one like full piece, then you don't have to worry about that multiplying by 2. But because the design of my aircraft includes, as you can see, there's 1 and there's 2, and if we do this for one, we have to do it for the other one too. So now that we've filled out all of our conditions, we can now estimate our drag. So drag is going to change with velocity. As you can see, the Reynolds number is increasing. So if I go over, um, so 54, that is associated with 20. So then 55 is 25, etc. So if I go over here, we can see that our total drag is 0.17 pounds, then 0.175, then 2, etc. So that's at 30 feet per second. And then let me convert that to miles per hour really quick. Because what we're going to do, 30 is 20 miles per hour. Okay, cool. So what we also need to do is we need to pull up our data for our propeller using our RPM and kind of find the thrust at our velocity. I'm lucky enough that I have an RPM really close to 7,000, 7,013. So I'm just going to use 7,000 as my basis. Something in between, I would recommend you guys interpolate, kind of figure out which would maybe, do an interpolation between 7,000 and 8,000, kind of similar to what we did for RPM in order to find a good medium. But as you can see, we're interested in this column. So as you can see, at 20 miles per hour, we have 0.887 pounds of thrust, which means we can increase our speed from there. So go here, so 20, 30, 40. I'm going to try 50 feet per second. So 50 feet per second is 34 miles per hour. 34 miles per hour. We have 0.504 pound force of thrust. Sorry. And so, yeah, it looks like we can go anywhere between, and then if we step it up to 0.48, that's 35, or 55, sorry. 55, which is 37 and a half. 37 and a half. Goes up to 0.396. So yeah, I'm going to use 34 miles per hour as my speed. And then so 37, or 34 miles per hour. And then I'm going to convert that into meters per second. So around 15 meters per second. Now I can go back here. And now we've determined a proper cruise speed.